Okay, homework 8. So we're skipping chapter 6, section 4, and going straight to 6.5. 6.4 is basically just calculator stuff. Plug this into a calculator. And it introduces something I don't want to introduce until we do it formally. This says just plug this into a calculator. I want to go in and talk about why we're doing what we're doing before you simply plug it into a calculator and trust what the calculator says. I want to talk about what it means theoretically. So we're going to come, we probably won't come back to this because like I said, it's just plug this into a calculator. It's basically no big deal. However, this is from 6.5. This is a very hard homework set. You can see it's long. It's the longest one you've had yet this year. It's not too bad, but it will take your time. Okay, it is no joke. Do not wait to start it. Do not wait to start it. Do not wait to start this homework because you will not finish it if you try to do it on Monday night. It's not going to happen. So, okay. Describe the following transformations of a function f. So,
shift it up one.
there you go, right? So we're gonna call this an upward shift, right? Or this is what last year we called this an upward shift, right? And in particular, right, you're adding to the output. This is the y value. You add to the y, and it goes in towards the direction of the positive y, right? However, what does this do?
Shifts it left to the left.
This is a leftward shift, right? So you're adding a positive number to the input, or the x values, you could think about it that way, and it goes to the negative x values. But it's still a shift, but it's in the left direction, and yes, by 1 unit. Okay, so then what does this one do?
Down and down.
It's a downward shift by 1 unit, and this is a what? Rightward shift. Again, the opposite. It's the opposite way that you'd think. This is intuitive, and this is what you imagine. I subtract from a y value, it goes down towards the negative y's. I subtract from an x value, you'd expect that it would go towards the negative x's, but it does the opposite because you're messing with the input. And we talked about that at length last year. Okay? Now, what does this do?
Stretches it vertically.
A vertical stretch, and in particular, away from the x-axis, right? And so it shifts up. If you're positive, it shifts you further positive. If you're negative, it shifts you further negative, and we call this a stretch, right? And it shifts away from the x-axis. Because if the output value is actually 0, right? If your function looks like this, right? And you're right here, that's your f value. F of x pops out as 0. Multiply it by 2. It doesn't go anywhere, right? But this guy who's up here at, say, 1, multiply him by 2, well, he gets stretched up to 2, right? So all these guys get stretched up. All these guys get stretched down. But the things that are at 0 do not move, right? And so that's why we're saying it's stretching away from the x-axis, but the x-axis stays put, right? This should all be reviewed, okay? Okay, now, I don't think we covered this last year, but what do you think this does? Actually, let's do this one first. What is this? Because we had a name for it. What does this do?
It's a switch. Like, oh, it's a stretch.
The opposite of a stretch. We called it a compression, right? So we're compressing in this case because, right, we're multiplying by something smaller. And just like my last example, right, if you're up here, that's your output value, and say it's at 2, you multiply it by 1/2, well, you've brought it down. Ditto with all these guys. And so we called this a vertical compression. And I do actually want to say this. So we called this a vertical stretch. This was a vertical compression. Again, towards the x-axis, because if you're actually here at 0, multiplying something that equals 0 by 1/2 is not going to change that you're still at 0. Okay, so
A horizontal.
So you mess with the inputs. Notice this has all been messing with the up and down direction. Thus far, this has been messing with the left and right direction, the horizontal direction. So what do you think this does?
Horizontal stretch.
You would think it's a stretch, but think about
it's
opposite.
Yeah.
Notice, right? This was an upward, this shifted you towards the positives, this shifted you away from the positives. This shifted you towards the negatives, this shifts you away from the negatives. This is a vertical stretch. When it's out here, it's actually, and it's not, now it's no longer vertical, it's going to be horizontal. This is a horizontal compression. Therefore, what's that?
A horizontal stretch.
It'll stretch you further out. And we're going to take a look at that right now. Horizontal stretch. Now these named shifts and stretches and compressions, these are pretty much it's not necessarily standard. I've heard it in a bunch of places in math. These are just my names for what it is. And I think they accurately describe what you see, right? And when you say compression, you know what I mean. So I like to use them. And so let's investigate this a little bit, because we didn't really talk about this last year, I don't think. And even if we did, it'd be good to go back over it. So, okay. So now, in the context first of, say, when f is equal to, say, sine. Pretty much, I think we've already done ones like these in your homework, right? Where you just take sine and shift it up by some amount. You take it, you shift it down, you stretch it. And we can combine those too. So like for instance, let's say we had the graph of sine. Here's sine x, we know what it looks like. It starts here, comes up, goes down, goes down, goes up to 1, down to -1. And if we wanted to graph, let's say 2 sine x plus 1, which order would we do? Because there's obviously a stretch and there's a shift. Which do we do first?
Stretch.
You do the stretch first, right? Because and the way that we trained ourselves last year to do this is you look at the function itself, like that's your output, and then you just ask what happens to it, right? Just by order of operations. If that were just a number, 3, you wouldn't add 1 to it and then multiply by 2. You'd multiply by 2 first. And so that's what happens to these outputs, is you have whatever the output is, you multiply it by 2 first, then you add 1. And so the first thing we need to do would be to stretch it, right? So we take our original 1 and we go 2 sine x. We stretch it up now to 2 and down to 2. Ditto here, right? And so it goes up to 2. Down to -2. And then we're going to add 1 to that guy. So what is that going to do to this graph?
It's going to be at 3 and -1.
There you go, right? And so the way I like to do it is I'd say, well, this would move up by 1. And so that would be right here at, say, 1. We'd go up, 2 would go up 1 to, just like you said, 3, down to -1. And this is where this guy would go, like that. And so on and so forth, right? So there's nothing new there. You're going to have to do plenty of that here in this homework, but that's nothing new, okay? This is.
Wait. If you multiply the input and the output by the same thing, does it just make it bigger? Oh wait.
We'll talk
No,
about
you would
that.
have to switch. Never. Wait.
Yeah. So, and what we've done. So, and last year we're working predominantly in this context. We're working with parabolas, and with a parabola, you have the case like, let's say you have f of x equals just x squared. Well, f of 2x would be 2x squared, which is the same thing as 4x squared. So you could even think about this as, well, that is the same thing as just a vertical stretch, right? Because you could see it as, well, you just took your original function, f of x, which is just x squared, and then you just multiplied it by some number. That doesn't happen anymore with sine and cosine. You can't just pull out something from sine and cosine. It doesn't work that way. And so we're going to have to really discuss this, which is what we're doing right now. So, okay. So we did that, and that's cool. Okay, now. Okay, so we talked about that being a compression, that being a stretch. Now let's see y. Okay, so let's take sine theta. And right now, I'm going to worry more about this first period. So here's theta. Theta is my input value. This guy goes up, goes down, goes back up. And it makes talking about what we're about to talk about is so much easier with trig functions than it is with like lines and parabolas and stuff like that. It just lends itself to this much better. Actually, yeah, let's put another one in there, minus pi over 2. It's down to -1, goes up to 1. Okay. Is that accurate? Did I do that right?
Yeah.
Okay. So now let's say we wanted to see what sine 2x looked like. Okay, so we've taken the input, we've multiplied the input by 2. This is like our f of 2x. This would be what would it be? How would it change this? What were the words that we just used to describe it?
It's a horizontal
It's a
compression.
horizontal compression. So what I imagined then, what goes through my head here is that this stuff here gets smashed down this way by a factor of 2. This stuff that's over here gets smashed down this way, just like it was with the vertical compressions, right? Everything comes in closer. The same thing's going to happen here, but it's coming in closer to the y-axis. Okay. Now what I want to do now is say let's think about it this way. So let's think about the original theta. Is that what I wanted to do? Yeah. Okay. So the original sine theta, this is the thing that we know, that we love. We've been doing this for a while now. You should be able to, just in your head, if you say, what's sine of pi over 2, you have this in your head and you go, well, this is where it comes up, and so the output is 1, etc., etc. And so now, what I want to do is this. I'm going to say, let's just substitute here. For right now, let's pretend that this theta is the same thing as 2x. Now check out what happens.
And it wouldn't do a sine.
Well, but it's going to be, yeah, right. But now the question is, I'm going to start plugging in values for x, because I'm going to try graphing this guy. Now, first thing to notice is what happens when I plug in a 0, when x is equal to 0.
It's not
1.
0. No.
It's just 0.
It's just 0, right? Like, this becomes 0, and it's exactly the same thing as this. Kind of like what happened when we had a vertical stretch and you were on the y-axis, right? If you're on the y-axis, you're not moving, right? And your stretch is going to make this bigger, it's going to make this big, it's going to stretch it away, but this point doesn't move. Same thing with horizontal stretches. We're here, we're at the y-axis, and everything's coming in towards the y-axis. The point that's on the y-axis doesn't move. Cool. Okay, so now check out what happens. When x is equal to pi over 4. So now we're going to graph what happens here at pi over 4.
Oh,
Well, now let's think about this in terms of our original function.
So it's the same. Oh.
So since theta is equal to 2 times x, we have theta is equal to 2 times pi over 4. And what's 2 times pi over 4?
Pi over 2.
Pi over 2. And therefore, what's the output when I plug this guy into there? What do we get? It comes out as 1. And we could go through and do this with all of the previous ones, but let's do another one. Let's move out a little bit more and go pi over 2. When x is equal to pi over 2, theta is equal to 2 times pi over 2, which is what?
Pi over 5. Wait, no, pi. Yeah.
Pi. And so by the time we get to pi over 2, this guy has already come back down. One way of thinking about this is like, because sine doesn't care about what's going on in there. All sine cares about is what number are you actually putting in. we know that we're actually throwing in a pi over 4. But as far as sine is concerned, he's going to say, well, when you plug in a pi over 4, I don't see that. All I see is this, like you've done this, and now this is the thing that goes into sine. And we know that when you plug that into sine, you get out a 1. Right? And ditto, we could keep going on and on and on. We have 3 pi over 2, then theta is equal to, 3 pi over 4. If I plug in a 3 pi over 4, because you see what I'm doing here, I'm counting by pi's over 4. 1 pi over 4, 2 pi over 4. When you're at 3 pi over 4, theta is 2 times that amount.
So 3 pi over 2.
So 3 pi over 2, and that we know is -1, so this guy comes down. Well, the way I like to think about what's going on here is when you multiply this by a number, when you multiply the input by a number that's bigger than 1, you're kind of speeding up how fast this happens. Right? It used to be the case that when we were back here in theta land, it took me pi over 2 seconds to run to the top of the hill. But now we're doing everything twice as fast. That's one way of thinking about this, is like you're speeding up how fast you're running. It used to take you pi over 2 seconds to get there, but now it only takes half that time. It takes pi over 4 seconds, and so on and so forth. That's one way of thinking about it, right? Finally, the last one we're going to do is when x is equal to pi, and theta is 2 times pi, which is just 2 pi, and so we're back to where we started.
Did you just divide everything by the coefficient of whatever?
Yeah, that's this is one thing we are going to get to. That's exactly so right now we're just investigating why it's the case that because like you said it, well, that should be a stretch. You're making it bigger. Yeah, but it's the opposite, right? The things that go into the inputs do have the opposite effect of what you think. And so I'm just talking about why right now it is that way. And it's because of this. Like you go through and do this point by point and see like, oh yeah, that is what's happening. Sine doesn't care what you're putting in there, right? There could be any function in there in the world. All he knows is whatever that output happens to be, that's the output I'm going to do. You happen to throw in a pi over 4, I didn't see that. All I saw was pi over 2. You know what I'm saying? So we could do, I just want just to get this all on the board real quick. I also want to do the opposite direction. Why is it the case that this guy, sine of 1/2 x, should be a what?
Stretch.
In which direction?
Horizontal.
Should be a horizontal stretch, right? And so, let's see why. Again, it used to be the case that I'd have to wait until pi over 2 to get all the way up here. But now I have to wait even longer, because watch what happens. When x is equal to pi, now, what are we computing? Sine of 1/2 times pi, which as far as he's concerned is just sine of pi over 2. And so now when we're all the way out here at pi, he says, we finally got to the top up here. Right? And so that's why it does that. We can keep going. When x is equal to 2 pi, then we finally get to sine of 1/2 times 2 pi, which is sine of pi, which then finally comes back down here, and so on and so forth. So as you could see, or you could think about it as, well, you've slowed down the inputs, right? Like here's the inputs going like 1 radian per second, right? Now here you're taking your inputs and you're slowing them down. So it takes twice as long for this same thing to happen as that happened over there. Does that make sense?
Yeah.
So we don't need, and now that we believe this, I hope we believe this, we could just keep it in our heads that what this does is pushes it in, and in this case by a factor of 2, so where you were at 2 pi, you half that, and that's how long it takes, and so on and so forth. And everybody should be exactly that same way. If you multiply your input by a number that's smaller than 1, you've slowed it down so that stretches everything out. Okay? So, all right. Okay, easy enough. Now, get ready. You'd be like, well, yeah, that's what I'm about to write up here. You'd be like, well, obviously that was the next thing that we're gonna do. Yeah. It's just, oh man. And you think, well, yeah, okay, I think I know what to do. And it's just so counterintuitive what's about to happen here. Okay? Okay. So there are two things going on, both happening to the input. There's obviously a compression or a stretch, and there's obviously a shift of some sort. And like, right? Right? So like, we just did this, so you know that something just is going to get compressed, right? Yeah. We know from last year that when you take your input and subtract off from the input, it shifts it in some direction. That's cool. But I want to keep ourselves honest here. And in order to do that, I want to find out what happens when x equals 0. I want the output value so that when we have our final picture, we can check and see what happens when x equals 0 to see if everything's true. So let's just plug in a 0, and what do I get? 2 times 0.
Sine of minus pi.
There we go. So it's just sine of minus pi over 2, which is equal to what?
Negative.
Yes. And if you're savvy, what went through your head was something like this. And you went, yep, there's minus pi over 2. That's a negative 1 right there. I know how to draw this. I could draw it in my sleep. And so, yes. Okay. So we're just going to put that on the board just so we can check, because we're going to do a bunch of shifts and all kinds of crazy stuff. And I want to be able to check that when we're done doing our shifts, that's what happens. So now let's try the obvious way. Let's just do the order of operations here. Let's just say, okay, you have your input. The first thing that happens is the compression. The second thing that happens would be a shift. So let's do that. Let's do that this way. We're going to start with just regular old sine. Okay, so we have regular old sine that does this. This happens at pi over 2. This is pi. I'm going to do a little bit over here too. Why not? There's minus pi over 2, and there's minus pi. Everybody with me? This is just regular sine x. Now let's do the compression first. And say, okay, therefore, sine 2x, well, we just did it, but let's do it again. It just compresses everybody in. And you'll notice I'm not going to bother to like make it look more compressed, because it's going to get ridiculous if I try to do that. But what should this point be right here? That's pi over 4. Oh. And this point is what?
Pi over 2.
There you go, pi over 2.
Wait, isn't it pi and... I thought it was slow.
We've
compressed
it, right? Compressing. Everything's happening. We're speeding it up so it happens fast. I know. Yeah, I know. And this is what I'm saying. There's a lot of different ways you can think about this. But one thing that's going to be kind of important. You probably want to keep track of these as you go on, because in this case we're not multiplying this by anything. So I'm going to introduce this right now. Its amplitude is 1. Okay? So with all of the trig functions, right, they go up to some max and they have some min. And let's say it goes up to 3 and down to negative 3. Then its amplitude is that distance right there. It's amplitude. Amplitude. And you could easily see, given a trig function, you could see that its amplitude, you have something like that, its amplitude is whatever number is right out there. Okay? We'll return to that in just a second. But I want to go ahead and just have that up there. So its amplitude has stayed the same. We haven't stretched it vertically or compressed it vertically. The only thing that happened is we had a horizontal compression. That makes this at minus pi over 4. Now we're doing the naive thing, right? Or the obvious thing. Just like, hey, naive doesn't mean that it's stupid, right? It just means, well, like we're going in here uninitiated. I don't know what to do. Let's do the compression first, then we'll do the shift. So we did the compression, now let's do the shift. So that shifts in what direction by how many units?
The
Right.
It moves to the right because it's opposite by that many units. And so by pi over 2, there's pi over 2. So we should have this hump, it just moves over like this.
Like goes.
This guy comes down like this.
Oh,
And now let's ask ourselves, could this possibly be right?
What?
No, wait.
No, when you plug in a 0, we know we're supposed to get out a -1. And so, and I'm going to go ahead, yeah, and so this is not the way to go.
Because
We cannot simply say, let's use order of operations here. Let's just, so in other words, what we did is we looked at this and we said, let's do this by a series of shifts and stretches and stuff like that. And we said, let's say that the order should be, well, there's my input. So the first thing that happens is this. The second thing that happens is this. And this is indeed what we've drawn. We've drawn, or we've tried to. This is the question. Is this equal to this? And it turns out it's not. Because we know that, well, let's just plug in a 0 here. Plug in a 0. You get out sine of pi minus 2. Sine of minus pi over 2 is -1. Uh-oh. That's not right. This is not right. Uh-oh. So let's think about this now. When we added to the output, it went up. When we added to the input, it did the opposite thing. When we multiplied the output by a big number, it stretched it. When we multiply the input by a big number, it does the opposite thing. So maybe the order of operations needs to be opposite too. Because think about it, right? As far as sine is concerned, right? Like think about it like this. You have your foot, you put on your socks, then you put on your shoes. But this is what sine sees. Sine sees your shoe, right? Sine looks at that and says, I see a shoe. It's going to have to first take off the shoe, and then it sees your sock. And then it says, okay, now I'm going to have to take off the sock, and now I'm down at the foot. Okay, that's my foot. Okay, right? So it's in the same way, like the input is opposite from the way that you think it is. That's what's going on here. That's why this didn't work. But what is going to work is if we do it in the opposite of the order of operations.
So
Now,
Sally and excuse, please. Wait.
oh no, please no, don't. So because now here's the thing. We're going to do it this way. This is not the way I'm going to recommend to do it. There is a better way. But and this is strange for me. Where did I want to say this? Yeah. There is a better way. Now I prefer to build on the stuff we've done before, and this is the way we had been doing things before, right? We have shifts and stuff, and we have these principles of these tools we've built up over the last year. And I like to do that instead of usually a book has a shortcut for how to do something simply. And I don't like that because I like using all the tools that we've built up. This is the one time where I'm going to recommend using the book shortcut because the book shortcut is very cool. And there's some cool stuff behind it that we're going to talk about. But right now, I do want to finish this up. I want to say, this is why this didn't work, is because as far as sine is concerned, he has to take off the shoe, then take off the sock. Okay? So in other words, we start with sine first. And from here, now we have to look at what is sine of x minus pi over 2. So we do the shift first. And what does that do to this graph? To that graph?
That's what we had at the bottom. Shifts it to the right.
Yeah.
It should shift it to the right by how many units?
Pi over 2.
And so where does it cross the x-axis or the y-axis?
-1.
Negative.
Oh,
Zero. Origin.
Here's pi over 2.
Wait, no.
Yeah, careful. Don't look at this stuff. Don't look at this stuff.
Oh, right.
Because this is what I'm saying.
Yeah.
The first thing we have to do, we start with sine, then we take off the sock, right? Or take off the shoe, man. The last thing. We have to do the last thing first because it's inputs and it's backwards from what you expect, which is a real pain, which is why we're not going to do this method. But I want to show that this is what is happening, right? As far as sine is concerned, it's like you're giving me something, and it's been shifted by this many units. So I know how to deal with that. I know how to shift by this, and it moves in what direction?
To the right.
To the right. And so here's
-1.
negative pi over 2. It moves over to -1. This bit moves to here, and then it comes up and goes down like that. And since that's been shifted, that was pi over 2, this is pi over 2. This was at pi over 2, it gets an additional pi over 2, and it's pi. And so on and so forth. There's negative pi over 2, and so on and so forth. Now we're going to compress it. And therefore, when we compress this guy, again, very confusing because you're like, well, if I want to compress it, don't I multiply that entire thing by 2? Yeah. No, that's why we're not going to do this method. But now that we've compressed it by 2, this moves to what? It was here, it moves to
Pi
what?
over 4.
Pi over 4.
So
Now it does that, comes up, comes down. This was at pi, and so now it's where?
pi over 2.
There you go. And so on and so forth, and we could do this with all the others. It was at negative pi over 2, so now it's at negative pi over 4. And this is how, if you wanted to do it in a principled manner, the way that we've been doing, building on all the tools we've been doing with shifting and stretching functions, this is how you'd have to deal with an input. But there's a better way. There's a much better way. And we're not going to do it this way. But I want to keep this picture up here because this is what it is. And we can look, is it true that if I plug in an x equals 0, I get out a -1? Yeah. Yeah, it worked. At least that one point worked.
It's like negative cosine.
It's like negative cosine that's been squashed. It is the same thing as negative cosine 2x. So, okay, so here's the thing. This is what we're actually going to do. This is the way the book says to do it. It's a shortcut, but I like it. I think it's excellent. And it's one of the few shortcuts in a book that I'm going to say, yes, take it. Let's do this. So, if we have just regular old sine theta. Theta, one full period of theta is between what two numbers? I mean, you could choose any two numbers, but in your mind, as you think about the trig functions, what are some obvious ones?
0 and 2 pi.
There you go. You know that as far as sine is concerned, if you let theta range from 0 all the way up to 2 pi, those are the inputs that you throw in, then what you're going to end up doing is graphing out one full period of sine. And the cool thing about sine, because all of these guys, they're periodic. If you have one period, you just repeat it over and over again, right? And so you get the whole graph, the entire graph, if you could graph one full period. So that's the idea behind all of this, right? That's what we want to do. We're going to use this fact. But now it's not theta that's going into sine, is it? What is the input to sine in our case?
2x minus pi.
We're looking at 2x minus pi over 2. And so, let's just do this. So it should be the case that we will get one full period if we could figure out where on the x-axis this ranges between 0 and 2 pi. Does that make sense?
Yeah.
Because remember, like I said, as far as sine is concerned, he doesn't care what you do before you actually throw the number in. If this evaluates to 0, sine's going to be like, oh yeah, we're at the origin, it's 0. If this whole thing evaluates to pi over 2, he's going to say, well, you must be at pi over 2, so my output value is 1, and so on and so forth. And so what we're going to do, this is how the book says to do it, and I want to elucidate this a little bit more than the book does, because there's actually some pretty cool stuff going on here. So the book says, now let's just solve for x. So what do I need to do to solve for x? In other words, we want to get x by itself. They're in the middle.
Subtract.
We need.
Subtract.
Minus pi over 2.
How about,
three?
Oh, it adds pi over 2.
let's add pi over 2 to everybody here. So we get plus pi over 2 on this side, less than or equal to 2x. Because this is the same kind of thing we want to set up here. Like, if we know that theta, this is like the range for theta, or well, this is the domain, right? This is the domain we're talking about. As theta takes on these values, and what should be going through your head is these values right here, from 0 all the way up to 2 pi, what you know you get is one of these. And so now we're trying to say, well, x is different, right? Because like down here, well, you could see what happens, like, but you'll get one full period, but not from 0 to 2 pi necessarily. What we can say is, well, let's find out the x values that give us this right here. And so now let's clean this up a little bit. What's that? How can I rewrite that?
Pi over 2. Oh, no, 5.
What?
5
5 pi over 2, because that's 4 pi over 2, plus 1 pi over 2 gives me a 5 pi
Get
over
the other
2.
pi over.
Can divide by.
And then divide by 2, we have to flip the sign.
No, that's for negative.
That's only for negatives, which, if it was a negative 2, you would definitely want to do that. In this case, it's not, so I've just divided everybody by 2, and what do I get over here?
Pi over
Pi.
4.
And over here?
5 pi.
5 pi over 4. So, what this says is that when x ranges between pi over 4 and 5 pi over 4, we should, sine, as far as he is concerned, is going to do the same thing that he does from 0 to 2 pi. Interesting. Another way of thinking about this, I want to do it this way. It's almost as though we have sine of some function. That function happens to be 2x minus pi over 2. What kind of function is that?
A line.
It's a line. Where does it go through the y-axis?
Minus pi over 2.
Is it slope positive or negative?
Positive.
So it looks like this, huh? That's what that thing looks like. It goes through here at minus pi over 2. Now the cool thing, like we could go ahead and like set the output equal to 0 in order to find where this goes through right here. We've already done that, haven't we? Like you could pretend that this side didn't exist and you just set this equal to 0 and that was an equal sign, and then everything that you just went through, guess what? You just solved for that value, haven't you?
Yeah.
Yeah, right? Like just pretend for a second that this side doesn't exist.
Yeah.
And that's an equal sign. What you've just done is you've solved for x. You've found the x-intercept. That's pretty cool how that works. On the other hand, what are we trying to do? We're trying to find this interval here. We know that this function maps some interval. We don't know what interval on the x-axis it maps, but we know that its output runs from 0 to 2 pi. In other words, the outputs we're looking for go from 0 up to 2 pi. So let's plug in 2 pi as the output to that function so we could find the input.
Oh, and then
But we've done that already, haven't we? Like, if you cover that up for a second and pretend that what you've just done is you said, well, I need to know where the output of this thing is equal to 2 pi. Well, pretend that's an equal sign right there. Pretend that doesn't exist. And what have you just done? You've just found where the output to the function is equal to 2 pi. And it turns out to be at 5 pi over 4. So, let's think about what we've just done. We have sine. There's some function that's an input, right? And what we want to graph this thing. The whole point is to graph this and see what it looks like. And the trick that the book tells you to do, it doesn't explain why this works, but this is what it's doing. You're finding the input values here, the input values to x that will map onto 0 to 2 pi. And let's just check that real quick, okay? Because remember what I'm doing here. My claim is that if I plug in a pi over 4, it'll be the exact same thing as sine of 0. And so let's plug in a pi over 4. We have sine of 2x minus pi over 2. We plug in a 2 times pi over 4.
So we solve for x, sort of.
We've basically, yeah. What's 2 times pi over 4?
2 pi over
2.
How about pi over 2? What's pi over 2 minus pi over 2?
0.
Oh.
So as far as sine is concerned, when you plug in a pi over 4, he thinks, oh, I'm sine of 0. I know what to do with that. Sine of 0 starts right here. And again, then you go through every one of these values. You just keep moving along and moving along until you get to the end. And let's see what happens when we plug in the end value. The last value we had was 5 pi over 4. So now you plug in the 5 pi over 4. What's 2 times 5 pi over 4?
10 pi over 4. Which is
5 pi over what?
2.
2
Oh,
minus
2.
pi over 2, which is the same thing as what?
4 pi over
4 pi over 2, which is 2 pi. And so, yeah. So, in other words, this sine, as far as he's concerned, says, well, as you run from pi over 4, whatever, all I see is that you've given me a 0 up to 2 pi. And so, graphically, like, I want to do this one more time. I'm going to get rid of some stuff up here at the top. Remember how we got this. This should be in your notes, so I'm going to get rid of this stuff up here. Basically, what's happening is this. We're taking some interval. We don't know what it is, but we were able to solve for it. And it goes from pi over 4 up to 5 pi over 4. That gets mapped into a new interval. When you plug that into this function, it maps it on to this function, or to this interval, 0 to 2 pi. And as far as sine is concerned, when you throw in this interval, sine knows what to do. So we took this function, 2, but we take this interval, throw it into this function, and it turns it into this interval. You take that interval and throw him into sine, and sine says, oh, I know what to do. That's this right here. The only problem is, or what has happened though, is this isn't at 0 anymore. This happens, this point here happens wherever this x value is. When x is equal to pi over 4, we're right there. And when x is equal to 5 pi over 4, that's what happens. Does that make sense?
Yeah.
That's what we've just done. Is that what we have here?
Yeah.
Yeah, isn't it? Right? We didn't complete this. We could have, if we wanted to. We could have completed this like that, and we would have found, well, we know what we just did. We just shrank everything. So that was pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 right there, which is exactly what this is. So that's what you're doing, and this is how I'm going to suggest that we solve these guys, or that we graph these guys. The first step, when you're given something crazy, is to say, okay, you know what, let's just start right here and find out where one full period of it is. I know that sine has a full period between 0 and 2 pi. And so I'm going to say, okay, 0 to 2 pi, but now I'm going to take that input and replace it and get it down so I could find this new interval, because I know that that new interval will map onto 0 to 2 pi and give me ultimately one full period.
What about tangent?
What interval would you use for one full period of tangent?
Negative pi over 2 to...
You could use any of them, and we don't have to use these. We could have gone from negative pi to pi. I mean, whatever, as long as the total length of the interval is 2 pi for sine and cosine. We'll talk about next section. We're going to do it with the other ones, but tangent, we know it's a total, it repeats every pi, so you could do it for every pi. The obvious one to choose is the one right around the middle, from negative 2 pi, negative pi over 2 to pi over 2, and that's what you would do there. So, okay, so all together now, this is how you would do this, and let's, because I want you to see how this is going to look. Let's get rid of this guy. And yeah, so again, we take our thing that we're trying to graph. We take the input to it and we put it between one full period. That's one full period. We solve to find that you get pi over 4 less than x less than 5 pi over 4. And now, that gives me one full period, so I'm going to go ahead and draw that full period. And guess what? Every one of these guys looks like this. Okay? Like, you don't need to try to squeeze it or stretch it. It always looks like this. It just matters, what are these points right here? And so what I like to do, this is the way I like to do it. I'm going to start with my one that I know, which should be the left one. And by the way, if that happened to be a negative pi over 4, I'd have some more work to do, right? Because then it would be, the question would be, well, where does it cross? Does it touch at the top? You'll get there. You'll have plenty of them like that. 5 pi over 4. And what I'm going to do is this. Now, this is where we're going to introduce a new thing. Did I do all this? I did all this. Okay, so.
Another 6.
So. For any function in this form, or in this form,
A times sign?
A times sine, A times cosine bx plus c. We have a couple definitions.
Yeah.
I already told you. A is called the what? Amplitude. This, it's pretty obvious what this does. It stretches it and stuff like this. The period can be found in the following way. You take 2 pi and you divide by the absolute value of b. So in our case, the period, we'd say, well, the absolute value of 2 is 2. You take 2 pi, divide it by 2, and oh yeah, lo and behold, yeah, that's what happens, right? It's always going to be the case, because no matter what your bx plus c is, that's the thing you're putting between 0 and 2 pi. That's your period, right? And so, yeah, you get your c out of the way, blah, 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 blah. Everybody got that? Then you divide by b. All right, we got to go. I knew we would not get through much today.
That wasn't mine. Oh no.
Oh, there's more. Or, well, it's not that. But that's your new period, isn't it? Like, that's how much, because look at this, right? You start at pi over 4, you add another that much to it, and that's how much you end up with. Or like, you could just think about it this way. This is how big your period is it not? Right? That's why we chose that. We said from 0 to what? Well, I could have said 900,000, but I didn't, because 2 pi is one full period. That was the whole point. Then when you end up dividing by it, that guy right there is the new length of your period. And so the period, the new period, for once you've transformed this guy, is what you get when you take your old full period and divide by whatever number that is. And so, in this case, it's going to be 2 pi divided by 2, and my new period is just pi. And then what I like to do is then, since I know that there's 1, 2, 3, 4 points from the first point to the last, or 4 bits that I need to mark here, I just take this and divide it by 4. I take the new period, divide by 4, and in this case we get pi over 4. And that's what I'm going to count by. So I'm going to go 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and then I use this as a check and go, is the next one really 5 pi over 4? Okay, I've done it right. You'll notice I did not bother to reduce these guys. 4 pi over 4 is pi. 2 pi over 4 is pi over 2. Don't waste your time. Don't waste your time. Just do this.
It's less
Your life is
right.
so much easier. And you get to check yourself and go, wait, did I do everything right? Well, I know it's supposed to go from pi over 4 to 5 pi over 4. I know that the full period is pi, so when I cut it into quarters, it should be pi over 4. So if I start here and count, I get 1 pi over 4, 2 pi over 4, 5 pi over 4, 4 pi over 4, 5 pi. Oh, yep, okay, I must have done it right. So then we continue it on the both directions and so on and so forth, but we'll get into that tomorrow.